Okay. We've got different mics for different parts of the range. So, um, thermal testing. Tonight's experiment, we have a hypothesis. Okay, so our hypothesis is if we have a fixed plasma, the value of the plasma is fixed, the power level of the plasma is fixed, voltage and current remain the same. If we adjust the temperature or the flow rate of gas in and out of the chamber, how will they affect the neutron output of the reactor? Okay? So we're going to have a starting configuration. Our starting configuration is we're going to have fixed voltage, low temperature, and low exhaust flow. And then we're going to switch it around and we're going to do...
Carl?
Yeah.
I can't see a PowerPoint. I'm not sure if that's just me or...
Hang on. What are you seeing?
I'm seeing, well, half of Mr. Fink and then half of you. So we're like from the view of the monitor. Your soundboard monitor.
Oh, well, that probably has to do with the fact that I haven't... yeah, hang on just a second. Thank you very much for calling that out. That would be a problem. Let's try that. What do you see now?
The PowerPoint and you.
Oh, there's just too many buttons. You know what I mean? It's just like trying to do that, be the technical director, and everything else. It doesn't work sometimes. Oh well. I got an extra twist in my cable here. I've got to get it. Out of here or... All right, moving on. So, actually moving backwards. The starting configuration is going to be fixed voltage, low temp, low exhaust. Then we're going to go do a 4-step procedure. We're going to take a reading here, and the next step is we're going to reconfigure and we're going to look at low temp, high exhaust. And then we're going to reconfigure and do high temp, low exhaust. And then we're going to reconfigure and do high temp, high exhaust. So 4 different configurations. And the question is, which way will the neutron output go on each of these? And how many different levels of neutron output should we expect? So, let's talk it through slowly and see if we can get our head around how we came to the hypothesis and what we believe is going to happen, and then we'll run the experiment. So obviously we're going to let some gas flow into the system, and then we're going to turn off that gas or turn it down so low that it's just barely seeping in. And we're also going to adjust the exhaust so it's just barely seeping out. Very, very small amounts of gas here. And we have this largely contained amount of gas in the chamber. Next thing we're going to do is we're going to light off the chamber to get a plasma in it. And that plasma is going to be at 50 kV at 0.005 amps. Can anyone tell me how many watts that is? Congratulations! You all just signed up to an electronics course I will teach later. And you're going to go through Ohm's law. Because we're going to assume that you don't know Ohm's law or Watt's law. In this particular case, the answer is 250 watts. Okay. And then we're going to add something to it. We're going to refrigerate, blow some cooling down on this thing, and drop the temperature way down. And we're going to wind up with a low flow, low temp. Now that's what we mean by that. We've got a low temperature in the chamber, and we've also got a low flow of gas moving through it. But we have a fixed amount of plasma, 250 watts, 50,000 volts, 5 milliamps. That's not going to change. And we're going to compare that to another configuration. And this one is high flow. And as you can see, we've got lots of gas coming in. We've got lots of gas going out. We got a bunch of gas in the middle. We're going to light that gas off, and we're going to add the refrigeration so it's still cold. So we're still low temp, but now we're high flow. Which one of those do you think is going to yield the greater neutron level, and why? Okay, back again. You're going to do a low flow, low temp, and then we're going to do a high flow, low temp. Anyone have a guess?
Probably the high flow because you have more material to do the reaction with?
Well, if the pressure in the central vessel remains the same, and by the way it has to in order for us to maintain the same plasma configuration, then all we're doing that's different is we're replacing that volume in the central chamber at a much faster rate than we were before. Can anyone suggest how that might affect neutron production? Okay, so we'll move on a little further. The next thing we're going to do is we're going to do a low flow at high temp. Now at this point we've taken the refrigeration away. We've just barely turned the gas on. We've just barely let the gas out. We've got a fixed volume of gas in here, and oh yeah, we turned the refrigeration off. Now the temperature goes from about 70 degrees right on up to close to 200 degrees. So we just shut the machine down, and it's cooking out. How do you think this condition, as far as neutron output, same amount of plasma, is going to compare to the one before it, which was high flow, low temp? And why? Okay, there's two things that we're working against here. The first one is outgassing. Contaminants, moisture, little bits of metal that get vaporized by the high voltage and the current flow. Load that plasma with ions. Those heavy ions, those heavy metal ions, short the plasma out. They draw a lot of power. They heat the reactor up, but they don't produce any fusion because titanium doesn't fuse. So what's that going to do to your neutron output?
Decrease it?
Absolutely. It's going to decrease it. So contaminants decrease. Now think about if I'm flowing a lot of gas through and I'm replacing the volume in here on a very, very high rate, how is that going to help the situation?
Well, because it's going to be pumping the things that are contaminating it out.
Absolutely, absolutely. We're pumping all that contaminated gas out and putting fresh gas in there, and we're doing it at such a fast rate that the contaminants don't have a chance to build up, and so consequently we have more D2 involved in the plasma, and therefore we should see a higher neutron rate. Okay, that's good at low temp, but when we change that around now and we do high temp, how does high temp versus low temp impact the reactor?
Well, it goes back to the contamination thing you were talking about. At high temperatures, the ions in the conflats come off of the conflats and become part of the ions.
So we have two contributing factors here. Low flow aggregates contaminants. High temperature expels contaminants from the walls and surrounding materials, and therefore also introduces these contaminants into the situation. So you've got two independent causal properties that are playing out in this that are causing the plasma to become contaminated and therefore ineffective in producing neutrons. Okay? So then what happens with high flow and high temp? Well, it'll be better. It'll be better because we are exhausting a lot of that contamination. Will it be as good as high flow, low temp? No, because that high temp is still knocking ions off of metal. That high temp is causing metal to vaporize, and so you're going to be seeing a lot more contaminants than you would be ordinarily. Now what we're going to do is we're going to catch 4 data points in this process and essentially create a graph. And on this graph we're going to see low flow, high temp, low flow, low temp, high flow, low temp, and high flow, high temp. And we're going to create a graph across 2 quadrants. So it kind of should look like an S. It's going to come out, it's going to go down through the center, and then it's going to go out this direction or something. Now let's just see. If I've got low flow at low temp versus low flow at high temp, I'm actually going to start out with my neutrons more over on this side than on that side, right? So my curve is going to start out over here, and as I go down and I head towards high flow, high temp, right? I'm going to wind up low flow, I'm confusing myself. Someone rescue me here. Let's see. High flow, low temp is our highest neutron point. Where's our secondary? High flow, high temp.
Well, it depends, right? Which either the flow or the temperature. We have to figure out which one affects neutron output more.
Yeah. So that means we actually have to perform the experiment. So that's what we're going to do. We're going to go to the lab, and we're going to actually walk through the steps of trying to do this and catch those 4 data points.
What values are we going to use for, like, what categorizes low temperature, high temperature, or high flow?
My intent is to come in, low temp is around 70 degrees at 50 kV at 5 milliamps. Okay, I replaced those thermocouples today and seated them where I'm hoping, cross your fingers, they're in the best possible place. And I've also, prior to the experiment, I made sure they lined up. So when I look at them both together, they're both tracking on the same degree output. They're both telling me that the cooling waters without a plasma is the same. So because we moved the sensors and we haven't done any testing since, anything could happen. But we won't know without trying. So that's the next step. Okay.
Do we need some people taking data?
Yes, there's a as is evidenced already. It's easy to get confused on this particular one. So I would appreciate it if we've got some folks taking notes, and I'm going to go to the reactor, and I'll see you all there.
Okay, we need some online people to volunteer to.
Okay, everybody should be seeing a reactor room, and we're all filling into it and coupling up our hoses right now. Do you folks at home see the reactor?
A couple of you grab stools from the lab so you can sit.
Yeah, I'm seeing the reactor.
Good. Okay. Good, good. Okay. Okay, so one of the other things we're going to be looking at, this is the neutron meter, and you folks should be able to see that at home. You're going to be writing counts down off of that meter. And the other thing you should be able to see is this is our DAC control board, and we will be looking at power information and gas information coming off of here. So we'll get We'll get started here by bringing up a plasma. Everything should already be in fairly good shape. I'm going to drop the temperature down considerably more than it is right now. Let's see what we got. Christina, what's our conflat temperature front and back? Okay, Christina, you're going to need to turn your radio on.
Sorry, 68, 69.
Okay, we're starting out at 68 degrees. I'm turning on the refrigeration before I turn on the plasma so I can get a head start on it. And I just set it for about 59 degrees. So it will start down. And so now we're going to fire up the fusion. We'll begin by putting our gas at 4, and you can see that our gas is now rising up 3.5. Chamber pressure is about 3.8. We'll go back to the main page. High voltage is now armed, and we'll go ahead and fire it off. Okay, and we are at 25,000 volts. And that temperature bar you see in the middle of the page between the graph and the white circle, there is a purple, green, yellow, red bar there. That bar, the purple portion, is what's telling you what the voltage is. And we're going to go on up to 50,000 volts.
And we're at low flow right now?
And we are at that's a very good question. Let me see what we've got. No, we are at high flow.
And are we still changing the output valve through what we calibrated on the...
Yeah, I think what we'll do here is I'm going to stop at 50, and I'm going to go ahead and I'm going to make some tweaks to get us further up the scale on high flow. I'm going to start by, we'll run some more gas in, and then I will I'm going to actually turn the vacuum up. Okay, we'll run some more gas in. And I'll turn the vacuum up. I'll run. Okay, I am now at 50, at a full 5 cc's a minute. That is the maximum flow. if you look at the chart, you'll see the maximum of flow of gas that I can put in there. I'm at 5 cc's per minute. And yet we're still at 50,000 volts. So that's good news. Now at 50,000 volts, we are at high flow, low temp. And now we're going to take a look at our neutron. Okay. So now we're counting. We've got something blocking someone's head. Something? No, it's you, Dave. Careful of the camera, please. Okay. So you folks at home are watching the neutron count. See, the second camera's up there. And again,
So since we've got the refrigeration on pretty high, are we doing high gas flow, low temperature first?
we're getting, right now we're getting low temperature and it's high flow. And this actually, I anticipate, will be our highest neutron count for the night. 31,784. We're going to run it again. But that's what it came out, 31,784. We'll do a second pass. Did you get a chance to talk to your teacher about the p-value?
Yeah, I sent you an email right before I came here. So I'm prepared to do the calculations after we have the data.
Okay. My only concern is, are we capturing the right data? That's okay. So we may do 2 iterations tonight to give some repeatability, and hopefully that'll provide you some measure. Okay, we are crossing 19,000.
We have a black screen. There's a black screen.
You have a black screen right now?
Yes.
Okay, we apparently dropped power on the camera somehow. Yeah. Thank you. Okay. Dave, why don't you squeeze on over behind her? What I'm going to do, I'm going to take your air and we're going to plug Dave. Dave, give me your hose. And then you stand back behind her. Okay. What did that second one come up to be? We're at 29 5:45. How did we stayed at 50 kV. Okay,
The temperature went up a little bit.
temperature is 75 degrees. Interesting. So temp went up. Let me try to drive it down some more. Okay, we're going down to about 41 degrees in our cooling water. Now, just because the cooling water is at 40 degrees doesn't necessarily mean that our conflat is at 40 degrees. Because the cooling water is flowing in there, it's transporting heat away, and the colder it is, the more heat it will take away, but it doesn't follow that the temperature of the cooling water working against the heat of the plasma, the two combined are going to create the ultimate temperature of the machine. So we've got a couple of forces at war, and actually there is no way to know for sure. The temperature will actually vary from the impact point of the plasma to the place where the heat sink is making contact with the steel. All through that piece of metal, there will be a variation of temperature between 41 degrees and whatever the temperature of the plasma is generating. Since we don't have a way of finding that, we can get close. So right now, 50 kV, okay. Now we're going to head for low flow, low temp. So I'm going to reverse some settings here in the vacuum, but we're going to stay at the same plasma level. So again, we're running at about 50,000 volts. And what I'm going to do is I'm going to 5. I'm going to drop this down and start backing the gas off, and that'll turn it around. Dropping this off, and we're just seesawing back and forth. And we're going to try to get to a 50,000 volt plasma at the absolute minimum amount of D2 we can run. Okay, our flow is now very low. be right down here to 1. I'm going to stop at 1. Okay, so we're just right at 50,000 volts. And we're going to do another neutron check. Let's take a look at our temperatures. We are still right close to 75 degrees. So now we're running the neutron count. And again, this is low temp, low flow. The first one was low temp, high flow.
The voltage is a little low.
Okay. It's really hard for me to get it stationary there. Okay, we got 23,887. 23,887 on our first pass, and I'm going to do a second pass now that we've actually been here a little while. We will ride the gas. Stay as close to 50,000 as we can. You can see what following that kilovolts is a real challenge. And that's because it's kind of like flying a plane. When you slow the plane down, your control surfaces don't work as well. And it takes a significant amount of control, and you can very easily over control the aircraft. And that's what I'm seeing here right now. It just takes a minor. And of course, these rubber gloves aren't helping. Okay, how are we doing here? I see 23,887. As we look at the kilovolts, you can see we've got wiggles, but we're within 5,000 volts, 4 to 5,000.
I don't think you ran it again.
Okay, you should be seeing the DAC right now. You should be seeing KVDC, are you?
Yeah, I was referring to the 23,887.
Okay. Okay, 23,887.
Yeah, that was our first trial for this low gas flow, low temperature. Are we going to do a second one?
I'm
Yeah.
pretty sure when you press the button, it didn't actually reset.
Oh, thank you. Okay, we'll hit the button again. Thank you for catching that. Helps to have a whole set of eyes looking at this. Okay. $28,510. $28,510. And as you look now at the DAC, we look at the voltage. We've stayed pretty close to 50 kV. And our temperature is still right at about 75 degrees. So we're close enough. So temp hasn't made a significant difference. Our plasma has been fairly steady, but we have gone the full range of gas from 5 cc's per minute down to 1 cc per minute. So we have seen now the effect of low flow to high flow at low temp. Now we're going to shut the refrigeration down after I bang my head on the servo motor. And we're going to let the temperature climb. And it should climb fairly quickly. In fact, I'm going to give it good reason to climb. I'm going to help it along a little bit. To do that, I'm going to shove a whole bunch of gas at it. Okay, so as you folks have been watching, you can see that now I've set the reactor up for about 70,000 volts, and that's just to throw a bunch of heat in there. Okay, we'll take a quick look at our neutron count at 70 kV as we're transitioning thermally. And we'll ask a fun question. You can see our temperatures are starting to rise. Okay, so you folks at home, if we've got 54,000, hello, 54,423 as a count, and on my transfer calibration on my probe it says 516 counts equals 1 microsievert. Somebody calculate for me how many microsieverts we're seeing at this probe right now.
About 100.
100 microsieverts. Okay? I got one more calculation for you to make. 1 microsievert, 10 microsieverts equals 1 millirem. So how many millirem do I have if 10 microsieverts equal 1 millirem?
10 and a half.
All right, so through our lead shield here on the front of this, we are seeing at this test point right here, we're seeing 10 millirem neutron production coming through our detector. Transfer calibrations are nice to have. Now 10 millirem is 10 millirem per hour. So I have to stand here an hour to experience 10 millirem. I'm only allowed 5,000 millirem a year. So tell me, how long will I have to stand here till I hit my annual dose?
Did you say per hour?
Yes, 10 millirem an hour. And I'm allowed 5,000.
So 500.
Okay, so I have to stand here 500 hours to get to my annual dose. How much danger would you say I'm in? It helps to know the various types of radiation and calculations and calibrations, so you know when you're standing in something you shouldn't, or it's okay to be there. There's a lot
Also,
of
actually, the number would be closer to 476. I rounded.
Okay. Okay, let's see. Interesting thing going on here. Let's come on down to our DAC factory. And what this is telling you is the conflat front and rear are no longer in alignment. That means that one of the sensors is floated loose. However, I can tell you which one floated loose. It's not the one at 100 degrees. So the front conflat, which is the one we're taking our measurements on anyway, seems to be doing what we want it to, and it's up over 100 degrees. We'll go ahead and add some amperage. I have turned the amperage up to 8, and we're going to adjust our gas now. Back to 70. What's happening is, as soon as I'm pulling gas out, contaminants are flying into that chamber so fast that it's shorting it back out again. Look at that. That's crazy. Okay, we'll go on to the main page and look at temperature. Now look at our temp. Our temperature is up at almost 120 degrees. And crazy as this sounds, we're going to begin with low flow. Look at the neutron drop. Okay, so we are just about 50,000 there. Okay, we're going to hit the button. So we are at 50,000, 125 degrees. And we're going to do a little snapshot here. And this is actually a low flow condition. I can't say that. What's happening is it's high flow because I didn't change my exhaust, but what we're saying is we're pulling so much contamination out of the chamber that I've had to lean the fuel down to 1 cc to keep the chamber lit. Okay, so let's take a look. We are counting.
Wait, so is this low flow?
I don't know what to say. I've got the exhaust at a very high level, and I'm actually shut the gas way down. So this is a condition that we haven't seen before. We're producing so many contaminants inside the machine, it's offsetting. We assumed that the amount of gas coming in would be the amount of gas going out, and that contaminants would be a relatively small amount of the volume. But we're running into a situation with the volume now.
That's because we have the temperatures.
You need to turn your radio down, Dave, a little bit. Not that radio. Yeah, that radio.
And the contaminants are being produced because we're running at such a high temperature.
Yeah, correct.
But the flow, if we define the flow as the amount of deuterium coming in, then you're definitely a low flow.
Yeah. One thing's for sure, I'm not going to be able to, at this rate of contaminant adjusts the other way. How do I get there? Okay, the front conflat is 140 degrees, and I'm sure the back one is too, but the sensor has floated loose, and so we're only seeing about 80 degrees. Okay, 31,317. I'm going to run the second pass now.
So we have the output valve as high as it can go, or just, I mean, a lot higher than we had it before.
It's a lot higher than we had it before.
So we probably won't be able to get to the 5.0 gas flow input because the output. But could we get to something in between?
Let's see. We'll try it. Okay, as soon as this is done counting, we've got our second number here, 29,114. Okay, we're crossing 140 degrees. Going back to power. Okay, so now I'm going to go ahead and drop this down, and we'll just start opening this up and just see how far we can get with it. Oh, there's quite a bit left. I might still be able to get there. Okay, we did it. I'm surprised. 140 degrees. But we have a lot more vacuum open at the high temperature than we did the low, because the volume of outgassing that's going on in there is just huge. It's really quite amazing. Okay, so we are at high flow, high temp. And we're going to start our count. High flow, high temp. That was a, see those? Those are explosions of little bits of metal vaporizing. And they contaminate the chamber momentarily. And they create an instability. That's a really interesting phenomenon. Um, temperature is at 160 degrees. And what's our count? 27,933. Very soon I'm going to be as wide open as I can be on that exhaust. Look at these spikes in neutron production. We jumped up to 1,000,000.
We're still on the neutron. Could you put us up on the screen?
Oh, I see. Okay, so running along at about a half. Oh, wow, there's a spike that went up to 70. Look at the spike. Look what it did. Took us up over 1,000,000 neutrons per second. Now, what in the heck? What would cause that? I saw a spike. It jumped up to 70,000. But our flow of deuterium in is constant. It's like a whole bunch of deuterium cut loose or something. That's a rabbit hole. We need to go down that rabbit hole at some point.
It seems to be much more prevalent now than at the beginning of the experiment, the fluctuations.
Yeah, there's a fluctuation in chamber pressure. Yeah, there's another spike. And there's a drop in pressure, a jump in amazing. Okay, we are basically out of exhaust room.
Should we do our second reading for this?
Okay, so we're going to do our second reading, starting the meter.
What's the temperature at now?
Temperature right now is 165.
The counter is blurry on our screen.
Okay, the counter should be working right now. Are you not seeing counting?
No, it's good. It was just blurry a moment ago.
Okay. Sometimes I can get the autofocus to fake it. All right, so we are at 29,344. 29,344. With these great big spikes. Look at the spikes, folks. Great big spikes jumping up above 1,200,000 neutrons. At 160 degrees. Wow. Okay. So at this point, we're going to just shut it down. I'm going to bring the cooling back on. Drop the gas off. the gas is down finally. Okay, so proving once again that real science is stranger than fiction. When you're working with a real thing, you often get stuff you aren't expecting. And that's where the learning comes in. You'd never see this stuff in a textbook. It wouldn't happen. Okay, what we're going to do is we're going to go back and have a debrief now and start making questions out of the data we've got, because there are some areas of research and some branches to this that don't fit our original hypothesis. And we're going to have to just do a postmortem here to try to figure out where we're at. We'll just let things cool. So if you folks had just returned to the classroom,
Send the stools my way. Proceed.
well, that's cool.
Yeah, great test.
Okay. Some other things are going on here. Kind of want to tell you about some of them. Come on down here, R2D2. Be my friend. Woo! Yeah. So this is a Canon still photography camera, nice little DLSR with flash. And he's real good at taking background pictures. And he's the background pictures he takes are UHD, so ultra high definition. And if you look over there on the computer console, you'll see that all the control screens got smaller. That's because that monitor wasn't there. That is a 4K UHD monitor that just wandered in the door last week. And the monitor that was there is now connected to the electron microscope on a swing arm. So now when you look at the images on the electron microscope, they're great, big, huge images instead of those little teeny things you were seeing. Now the little television screen that monitors the actual beam is still the way it was, but we capture and export images onto computer, and we can store them as PNGs or TIFFs or any one of a number of different formats. And some of them are quite large, and we can now see them on a 32-inch screen instead of a 13-inch screen, which is what we had. So that's going to be fun. That monitor can also pivot so that people on the electrical engineering bench can use it as a lab monitor for their PC and their rack to do interesting experiments. And what that is that's all part of a movement forward. We're going to be making some changes. And Caleb and I are working on this. He and I are going to get together tomorrow to have an in-depth discussion of how this is going to go down. But basically, we are bringing 4K UHD to this studio. And we're not going to be I don't anticipate broadcasting 4K anywhere because of bandwidth issues, but we are going to start doing some of our production in 4K because it's much higher resolution. You get a lot clearer images, and when it comes to certain aspects of science, you definitely want your records and your images to be as clear as you can get them, because you go to look at that stuff later and it's hard to make out what it was the students saw. So 4K will help get us there. I'm waiting for Black Friday to drop my major piece of change on a very nice camera. Well, I've whittled it down to about 4 or 5 that are full blown movie cameras that'll be great for this kind of work. The studio here, the live studio, this show that we do on a weekly basis is going to remain 1080p. We don't need 4K for this. And 1080p is still taking me the better part of 2 hours to upload and render. So, for a half an hour to 45-minute show. So, that's not a problem on a weekly basis, but if I did that with 4K, it'd be 4 times as long. So, I don't want to blow a whole day, 8 hours solid, waiting for this stuff to happen. That's a little out of reach. But we can take some very nice 4K images and then resolve them down to 1080p. And when we do that, we actually wind up with something that looks phenomenal. It really is very crystal clear, good images to look at. So it's clear to me that with COVID going the way that it's going, particularly here in Washington State, it's going the wrong direction. Okay? And so I anticipate that the current distress isn't going to be over in January like everybody thought, isn't going to be over in July like everybody thinks. This is going to go on a while. And again, it's grassroots efforts like the one that we've got going here that offer hope from another direction that will allow us to return to some semblance of normalcy so that we can get on with our lives. It's critical that some of this research continues. The research that we're doing, the science research, absolutely. Because right now, what university is going to be able to offer you this? They're all shut down. My basement is good as it gets, folks. And it's sad that it's there, but right now at least we've got an approach to the problem, and everything that I'm seeing continues to validate that what we've decided insofar as the technology we're using and the way we're going about it is still the right formula. And so we're still going to stumble along here, learning as we go and making improvements and adding to our online capabilities and adding to our production capabilities. And again, 3 cheers for Caleb for stepping up to help me do some of this, because there's no way that I can continue to do this absolutely alone. I can't. You reach a place where you're stepping on your tail more times than not. Okay, so let's try to make sense out of this. Who is our official recorder?
I don't know about official, but I have the data.
Okay, you've got the data. Now we're going to make some summary statements about what's going on and also identify some questions that need to be answered. And this will be material that we're collecting for use as a post-mortem, okay? So, what was the first thing that we saw that was unusual? What comes to mind? Saw several things tonight. Come on.
Or the spikes.
Okay, so we saw some spikes. Let's what kind of spikes were those? Those are
It would go from like 200,000 to like a million neutrons and then right back down.
okay. So they were spikes in neutrons. What else did we see simultaneously with those neutron spikes?
We saw a spike in voltage and a drop in pressure.
Perfect, Christina. Dead bang on. You got them both. There were two things that happened there. We saw a spike in voltage and we saw a clear drop in chamber pressure. So, we have a phenomenon. The phenomenon is neutron spike, voltage spike, chamber pressure fall. Anyone have a hypothesis what would cause something like that? As I looked at the event, it would take place over, let's see, 5-10 second period. It wasn't just a real half second, 3/4 of a second blip. The pressure drifted down and drifted back up. The voltage drifted up and then came back down. There was 3, 4, 5 seconds of real time going by there when all these things were happening. One of the things that I said at the time of the event was, hey, maybe this is some metal vaporizing and contaminating the chamber. Wait a minute. If it was metal vaporizing, contaminating the chamber, that's going to raise the chamber pressure, not lower it. What suddenly causes the pressure in the chamber to go away? Blink. That's weird. That's weird. It doesn't have anything, if we said, well, there's potentially two things that could cause that chamber pressure to do what it did. There was a momentary lapse in the flow of incoming gas. That would be one. So that's something that we have to go look at. Is there some way that we can determine if the gas feed at that point in time, the cc's per minute dropped off? Can we see that in the data? there is a place to record that. In fact, the data is coming into the application. It's not being captured right now, but there is a place to go and look at that data and determine whether or not there is corresponding information, because we have, not only do we have something monitoring the chamber pressure, but the incoming valve is a mass flow control. And the way a mass flow control works is it's not just a mechanical valve. It actually meters the gas coming in, and it gives us a number as a feedback of that pressure. It tells us. So theoretically, during those events, we should be able to turn right around and look at the mass flow control and see if the numbers on that mass flow control are shifting. And if they are, then we know it was a gas input. Now, the more unlikely event is that something transpired that would cause a rusty brass valve. It's a mechanical thing in the bottom of this fuser to suddenly open up a bunch and then slowly close itself again. Not very likely.
But if there's a temporary blockage of the inflow of deuterium, that would lead to a drop in neutrons, not an increase, wouldn't it?
No, because the drop in pressure is actually how we raise the voltage. We actually deliberately reduce the gas to reduce the pressure to raise the voltage. That's one of the indirect ways that we control power. And so I would say the most likely explanation is we were experiencing momentary lapses in incoming chamber pressure. Now understand, that gas has to be coming in at the conflats. The conflats are now not 70 degrees, they're 160 degrees. Did that play a role somehow in the way that gas enters the chamber? I'm at a loss to figure it out. Okay, something else. What else did we see that was weird?
Well, the whole part about how originally when we were at low temperature, the gas flow input and gas flow output were equal, but then when the temperature was high, we had to have the output much greater than we did earlier in the experiment because of the contaminants that we were creating at high temperature.
Clearly, there was more coming out of that reactor than was going into it at the low temperature. And because I have no way to measure the outflow, because I don't have a mass flow controller on the output, I have no way of estimating, even proportionally, how much more exhaust it took to equalize the flow rate at those higher temperatures. But something major was going on. And it probably has been going on and dogging us all along, but we've never gone at the experiment this way, and so we would never have seen it. We just would have twisted the valve until it worked, not recognizing the valve was at a whole different location. Now, the funny thing about this valve is when you're opening it and closing it, yeah, we can count the number of turns or quarter turns or half turns, but that still doesn't give us an accurate representation of the amount of gas going out of the chamber, because the vacuum is going to vary with the volume of gas that's already in there. If you've got a higher pressure in the chamber, gas is going to flow out quicker than if you have a low amount of pressure.
Could we have the same setup for the exit that we have for the entrance?
No, because the size of the entrance is literally a needle valve. It is a very, very, very precise, small, little teeny needle that is controlled by this mechanism that allows air to go through it. Conversely, the exit valve is literally an inch or more in diameter. It's a great big pipe. And due to the nature of the vacuum pumps and the diffusion pumps that are below it, you have to open that puppy up several turns in order to experience the full effect of the exhaust. So they're disproportionate in terms of size, in terms of how they work.
Could it still have the measurements?
We need to ask some questions. Certainly, people have struggled with this before. Let's not reinvent the wheel and try to come up with this on our own. I think we need to, I need to make a call to Lexer or MDC, they're vacuum companies we do business with, and pose the question and say, we've got a problem with our exhaust system. We need to be able to quantify the amount of material moving out. What are some of our options? They'll be quick to suggest, oh, I promise you that. In 6 figures, they'll be quick to suggest. Oh dear. And then we'll have to figure out how we MacGyver something that'll do what they suggest. But yeah, that would be my first approach. But so we have the second phenomenon. Clearly, I was able, when we got up over 140, 150 degrees, I was able to have the exit valve set to the same setting that we had on high flow, while the input valve was set on the same setting we were doing for low flow at low temperature.
I've lost audio.
Okay, do you have audio now?
Yeah, I lost audio too.
I can hear you, Ankit, but I can't hear.
I don't think they can hear us.
Yeah, I
don't
can't
know.
hear Carl either.
Hold on, checking. Checking.
It says Carl's muted. It says you're muted.
Yeah, you're right.
Okay, we're working here to get it. Can you hear me now?
Yes.
Somehow
Yeah,
my
we can hear
mic
you.
was put on mute. That's what I just discovered. So I'm not aware that you folks even have the capacity to mute my mic from remote.
I think we do. Isn't it just right-click mute participant? I can test it right now.
Yeah, go ahead and test it. Yep, you can mute me.
Yeah, it worked.
Can you unmute me?
But I don't have the capacity to unmute you.
Okay. Somebody muted me.
This also happened, I think, last meeting.
Okay. Noted. Okay. Oh.
Oh, hello.
Hello.
Sorry, I wanted to pin your video again, and I accidentally clicked the. I didn't know I didn't even know that I could do that. I'm sorry.
Thank you. Just knowing what happened takes a load off my mind. Believe me, thank you very much
Yeah,
for your
I'm so sorry about
honesty.
that.
No problem. No problem. I've done stupider things, believe me. So, but resolving the mystery was huge. All right. Um, we have two phenomenon. Let's look at those neutron counts. Let me. We're gonna go. Okay. So Rishi, were you the one that was taking the neutron numbers?
Yep.
Okay. So what did you get for low flow, excuse me, high flow, low temp?
High flow, low temp. I think we ran 2 trials with that. The first one was 31,784, and the second one was 29,545.
So 31 and 29, let's call it 30.
Mm-hmm.
Okay, so 30,000. What did you get for low flow, low temp?
Also 2 trials for that. The first one was 24K. The second one was 28K.
Okay, so a significant drop, as expected. That followed our hypothesis. That's cool. So one of those two things. No, actually, there the only factor we changed was the flow. So when we went to low flow, we had more contaminants that it impacted the plasma. We had less neutrons.
The thing that gets a little confusing is it looks like we had basically the same neutron output for low gas flow, high temperature as we did high gas flow, low temperature.
Okay, we'll get there. Don't
Okay.
run ahead.
Sorry.
Let's go with the two that we did first. No. Okay, so high flow, low temp, and low flow, high temp corresponded to our hypothesis.
Do you mean low flow, low temp?
Low flow, low temp. Yes, thank you. So this guy and this guy did what we originally thought. Now, when we went to low flow, high temp, what number did we get?
They were around this. Yeah, they were pretty much identical to the high flow, low temp, around 30K, 31 and 29.
Okay, so low flow, high temp was high flow, low temp?
Yes.
Okay, so those two equaled. Interesting. Low flow, high temp. See, I would have thought that would have been our dog to eat dogs right there. That he would have been the lowest. Okay, and now what did we get for high flow, high temp?
Oh, also for a low flow, high temp, it was slightly lower, around 400. But I don't think that's a significant amount to.
No, 400 isn't enough to make a difference. Clearly, he's an outlier. So let's go to high flow, high temp.
Yeah, I only got one of the trials for that, and that was I got 27,900, so 28K.
All right, so 28K high flow, high temp, and that almost corresponds to our low flow, low temp.
Yeah, low flow, low temp was 26K.
All right, so this is 27, so within 1,000.
Well, and our second trial for the high flow, high temp was 29,000.
Okay.
So,
Yeah, between 23 and 29, I think, or
All right.
24, 29.
So my conclusion is that when we were looking at low flow and low temp and high flow and low temp, the gas controls were behaving as expected. But when we got up to high temp, all of a sudden we had this exhaust issue, and we also had these spikes happening. Now, stop and think about it for a second. I'm doing a neutron count. My average neutron number is 200,000, right? And I'm chunking along. I'm taking a picture over a minute at a time. All of a sudden, the number jumps up to 1,500,000. If it does that twice in a minute, what's that going to do to your number? Puh! You no longer have data, you have garbage. So, my conclusion is that the high temp readings that we took were impacted by stability issues with the gas flow and don't reflect the real nature of the experiment we were trying to conduct. And what we're going to have to do is we're going to have to diagnose what we're seeing at high flow, at high temp, and see if we can stabilize it. We're going to have to stabilize it before we can read it. But right now it's not stable enough, not reliable enough, not repeatable enough to call it good data. That's not a bad piece of science, though. That's very, very real world. We had a hypothesis. We constructed an experiment. We went in, ran the reactor. Real world stuff caught up with us, and all of a sudden, we've got work to do. Tell me when it hasn't been that way over the last 6 months. So, and that's great. That's real world science. That's why, we've been pursuing fusion for how long? Only 20 years. We've been at it 50, but yeah, it's only going to take 20 years to get there. That was 50 years ago. And they still haven't got it. So, actually, I'm pretty okay with this because I can see how the stability issues contributed heavily to these bogus readings. Okay. All right. Any closing thoughts or comments? Okay, action items. I'm going to take an action item to go explore high temp. And I'm going to be looking for exhaust issues. And I'm going to be looking for stability of gas input. And there is some place I know where I can go and I can look and I can tell whether or not it was the input or the output that varied. And I can conduct one more experiment and I will be able to nail it. And so I should, by this time next week, be able to tell you definitively whether or not we had a problem with our input or our output. But something dropped that chamber pressure. So, okay, 2 action items. We'll correct those, and we should come back and be able to run the experiment for the high temp side if we can stabilize that phenomenon. And we know that we've got one sensor that pulled loose. And I want to be able to marry up those 2 numbers. Okay, so with that thought in mind, if we don't have any more business, I'm going to go ahead and switch back to regular camera, and we'll start the egress.
Would you like for me to send you a copy of my data?
I would very much like that.
Okay, I'll send that.